In the last video we have discussed the scaling of the record efficiency from lab scale devices up to record module efficiencies. The objective of this video lecture is to discuss the relation between the record efficiency of modules and the efficiency of modules in mass production. Often the module records are achieved on research lab scale level using expensive manufacturing approaches. However, this does not imply that modules processed in mass production have the same performance as the record module efficiencies. All the advances in PV research, like a demonstration of record lab scale cells and improved manufacturing methods, lead to continuous increase in efficiencies of the modules and modules in production. A simple model to describe the evolution of the best efficiencies of PV modules in time has been introduced by Gutzberger. The efficiency evolution in this model is described by an exponential equation that approaches the efficiency corresponding to the theoretical efficiency limit. T start represents the year where the new PV technology was introduced, and tau development represents a characteristic development time of the technology. What can be seen is that in the early development stage, efficiencies improve rapidly. However, in a later phase, this evolution slows down. It makes more and more effort to make improvements and to get closer to the theoretical best efficiency. In this later phase, the PV technology can be considered as a mature technology. It does not mean that it is competitive. Let's look at the module efficiency development of commercial products in the period 2007 to 2014. The efficiencies are collected from the reference given here in the slide. You can see that the advances are significant for the monosilicon technologies. Efficiencies went up from 13% up to 17% in 2014. Data are from modules from BP Solar, Kyocera, Bosch, Schott Solar, SolarWorld, Suntech, Trina, Jingli and Jinko. However, the evolution of efficiencies is not leveling off yet. As you can see, multicrystalline silicon has a similar efficiency improvement in time. The data of these modules correspond to modules from BP Solar, Kyocera, REC, Schott Solar, SolarWorld, Suntech, Trina, Jingli and Jinko. You can see that the absolute improvement of CIGS solar cells in a 6-year period has been 5%, which corresponds to a relative improvement of 50% in the performance of the modules. This shows that CIGS PV technology is not as far in the evolution as the crystalline silicon products. Data of the CIGS modules correspond to modules from Solar Frontier, Mia Soleil, Solibro and TSMC. The other calcosionide PV technology, cadmium telluride, has seen a similar growth as CIGS. All data in this graph is from the first solar modules. Advances in research and development in processing materials and devices on both lab scale and production level are responsible for the improvement in the performance on these commercial modules. If you project these efficiencies versus the demonstrated record efficiencies for modules, we see that still a lot of room for improvement exists. Monocrystalline silicon has the room to approach module efficiencies way beyond 20% in the far future. Multicrystalline silicon will have module efficiencies which are able to approach 20%, as you can see in reference to the record module efficiency for multicrystalline silicon solar cells modules. CIGS needs some important progress in certified record module efficiency to guarantee a long-term progress in module efficiencies, as you can see in this plot. Cadmium telluride still has sufficient room to develop further and stay competitive with multicrystalline silicon modules. The challenges to be tackled are the integration of new device configurations on module level up to the development of cost-effective processing methods to produce these new complex architectures on large scale. For example, the processing of the IBC contact in the heterojunction solar cell with record module efficiencies is not yet cost-effective. Another aspect to be considered is the source materials used to manufacture the modules. Are the materials abundantly available to produce large volumes? Abundance of ores also determines the cost price of the material and consequently the cost price for the module. For technologies based on silicon, like crystalline silicon and thin film silicon, the typically used materials are abundantly available, as you can see in this plot. For cadmium telluride, the tellurium becomes a scarce material. Therefore, companies like First Solar have to focus on the entire value chain to secure cheap and sufficient supply of tellurium. For CIGS technology, the challenge is the element indium. As indium is also used by the display markets, securing the indium supply is important for companies like Solar Frontier. For 3.5 technologies, no large-scale bulk volume production exists, so the scarcity of the material of indium does not play a role yet. In summary, we have discussed the improvement of efficiencies of most important PV technologies so far, but what about the cost prices? In the next video lecture, I will discuss the learning curves of PV technologies.